A pure semiconductor crystal is a beautiful, highly ordered structure, but as a component for precise electronics, it has a fatal flaw. Its ability to conduct electricity is entirely at the mercy of the ambient temperature. In this intrinsic semiconductor diagram, heat breaks bonds, creating thermally generated free electrons and positive holes. Because every electron leaves one hole, their concentrations remain perfectly equal. Ne equals Nh. Both contribute to current, but this thermal randomness is uncontrollable. To fix this, we have to intentionally introduce a flaw. As these notes explain, by adding just a few parts per million of carefully selected impurity atoms, called dopants, we can force the conductivity to increase drastically. By introducing these specific flaws into the perfect lattice, we transition the material from an uncontrolled intrinsic state to a controllable extrinsic state. We are hacking the crystal's conductivity. There are two distinct ways to hack the lattice. The first uses pentavalent atoms. These are elements with 5 valence electrons, like arsenic, antimony, or phosphorus. Here in this diagram, a phosphorus atom has replaced a germanium atom in the lattice. 4 of its valence electrons lock into the surrounding structure, but that 5th electron has nowhere to bond. It is instantly free to move and conduct current. We call these pentavalent impurities donor atoms. Because we control how many we add, electrons become the overwhelming majority charge carriers, vastly outnumbering the holes. This creates an N-type semiconductor. Now, look at the bottom note here. Crystal is neutral. It's easy to assume this material has an overall negative charge because of all those extra free electrons. But remember, the donor atom we added also brought an extra proton in its nucleus to balance that electron out. The crystal itself remains perfectly electrically neutral. We can track this physical change on an energy band diagram. The donor atoms create a brand new energy level, marked here as ED. Notice where ED sits. It is just 0.01 electron volts below the conduction band. It takes practically zero energy for those donated electrons to jump that tiny gap and start conducting. N-type doping gives us a massive, instantly accessible surplus of negative charge carriers, all while maintaining the strict neutrality of the original material. The second approach flips the math. We use trivalent atoms, which only have 3 valence electrons. Examples include indium, boron, and aluminum. Look at the lattice now. When an aluminum atom takes the place of a germanium atom, it doesn't have enough electrons to complete all 4 bonds. It leaves an empty space, a positive hole, right from the start. We call these trivalent impurities acceptor atoms. By adding them, holes become our overwhelming majority charge carriers, creating a p-type semiconductor. On the energy band diagram, these acceptor atoms create a new level, EA, resting just barely above the valence band. It is now incredibly easy for standard valence electrons to jump up and fall into these newly created holes. P-type doping achieves the exact inverse of N-type. Instead of a surplus of electrons, we flood the material with highly mobile positive vacancies that are desperate to accept electrons. Whether you choose to flood the crystal with electrons or holes, you are bound by one universal mathematical rule, the mass action law. No matter how extreme your doping is, the concentration of electrons multiplied by the concentration of holes will always equal the intrinsic concentration squared. Let's test how this law holds up in practice. Take a look at this problem. We have pure silicon at 300 Kelvin that we decide to dope with indium. Our baseline intrinsic concentration is 2 × 10 to the 16th. By adding indium, we push the whole concentration up to 4 × 10 to the 22nd. We need to calculate the new electron concentration. Pause the video right here. Face the daunting exponents, set up the mass action law, and prove you know how to calculate the state of this crystal. Then let's solve it together. Welcome back. We start by plugging our known variables directly into the mass action equation, giving us Ne times our massive new hole concentration, equal to our baseline concentration squared. When we square the right side, the 2 becomes a 4, and multiplying the exponents takes 10 to the 16th up to 10 to the 32nd. Dividing that by our hole concentration leaves us with a final electron concentration of 1 × 10 to the 10th per cubic meter. Notice how tiny that electron concentration became compared to where we started. By flooding the crystal with holes, nearly all the free electrons that naturally existed fell into those new vacancies, drastically reducing their overall number. We've covered a lot of ground. Here is a complete summary of the physical, energetic, and mathematical rules for intrinsic, N-type, and P-type materials, tied together by the mass action law. Grab a screenshot and use it to decode your next semiconductor circuit.